Yeah, so initially, I guess yes, I will. Also talk about silica. In fact, when I was thinking about kind of what should I talk about, I thought about talking about broadly opportunities to disrupt cloud storage today. But I kind of decided to mash two talks together that also talk about some of the stuff we've been doing in silica, some quite actually recent work which we haven't yet talked about publicly. So you're the first kind of audience to see some of that. But I guess first I'm going to start by painting kind of a broad picture of how we see the cloud storage landscape, how we think about storage technologies in our group, and how we think about why do we think there's why are we working on disrupting storage in the cloud. And then I'm going to focus in on silica, which is a archival storage technology. So everyone can hear me okay? Okay, so yeah, so I guess the spoiler to the title of the talk is yes, absolutely, there is opportunity for disruption in the cloud storage space, right? And primarily what started us thinking along these lines is, if you asked somebody 10 years ago, what are the dominant technologies in the cloud, people would have said flash, hard disk drives, and tape, right? And today, this is still the same answer, right? So we think that there are many reasons why this answer may be different in 10 years' time. So today, if you look at the cloud storage landscape yesterday and today, there's primarily three storage technologies: flash, hard disk drives, and tape. And these technologies were all invented before the cloud existed, before the cloud was a thing. And they were designed to operate in a number of different consumer and enterprise environments. And because of their vastly different properties in terms of performance characteristics, cloud providers end up offering these today in different segregated storage tiers at different price points. Each of these underpinned by a different technology. Flash over here tends to offer, can everyone see my cursor also? Flash tends to offer the highest IOPS and throughput requirements, but obviously this comes at a premium price. So this is where you would store your your database indexes, your key value stores. However, the majority of the data in the cloud actually resides down here on magnetic media. This is hard disk drives and tape. And despite popular belief, tape is in fact not dead and is very much still in active use inside the cloud. A natural consequence of this is that this hierarchy ends up being ordered by temperature, that is by access rate, with the least access data, so the coldest data at the bottom of the pyramid here, and the hottest data at the top here. And kind of the price also increases as you go up this pyramid. And if you look at this, all of these tiers have been expanding massively, driven primarily by the exponential growth of storage demand. So if you look at, this is just a kind of a cute picture just to illustrate a little bit what I mean by this crazy exponential growth, right? This is the Boynton, Virginia Azure data center, which is one of the largest data centers that Azure operates. This is what it looked like in 2014. In 2017, just 3 years later, this is what a small fraction it occupied out of all of the real estate occupied by the Boynton DC. And this is already just 5 years ago. Today, Azure has hundreds of data centers all over the globe across all of the geographical regions that it operates in, across all the continents. By 2025, it's estimated that humanity as a whole will generate around 175 zettabytes of data between the cloud, all of the edge devices, all of the IoT stuff that we're doing. And as you might guess, cost is a really crucial concern. So providers have to cloud providers have to cut costs in order to stay competitive. And hardware is a big part of that. And the problem is that in order to keep up with this exponential demand in storage, this requires the cost to also drop exponentially. So when providers purchase storage, they also expect the dollar per gigabyte cost to also decrease exponentially. which puts the burden on storage vendors to then drive innovation and decrease these costs in large volumes. And traditionally, for many storage technologies, cost is driven by density increases. However, for some technologies, and I'll talk a little bit about that, this progress is becoming increasingly difficult. Now, we use this framework called the S-curve to think about technologies as they evolve over time. So every successful technology tends to follow an innovation S-curve. So here on the x-axis, we see time. And on the y-axis, we see some metric of interest. For storage, this is typically dollars per gigabyte or dollars per IOPS. And every technology tends to follow three different eras. The first era is the era of ferment. So here, there is very little progress on this metric of interest. The basic physics of the technology are still being understood. And the technology is still very much in its infancy. But if you're able to make sufficient progress on understanding the physics, at one point you reach takeoff. So these basic mechanisms have been understood, and you're able to now scale this metric of interest very rapidly. So typically this is captured by some rule of thumb, like, the capacity will double every 3 years or so. Now, at some point, it becomes very difficult to keep improving these metrics, and at some point, the technology reaches maturity, and it's set to roll over. So it becomes very difficult to continue doubling density like this. Now, this point here is very interesting because at this point, the technology is very vulnerable because a discontinuity can occur. If a new technology can come along and make sufficient progress on this metric of interest, it can very quickly surpass the incumbent technology and become the default standard, right? So we've seen this over time happen in many cases with, cassette tapes replacing vinyls, CDs replacing cassette tapes and vinyls. Yes, there's a vinyl resurgence now, but this is for different reasons. Streaming replacing physical media. There's been many examples of this. This is just in the music space, but there's many examples of this kind of happening. So obviously, this is not a quantitative tool. This is just kind of a qualitative framework that we use to think about, where do different technologies exist in their life cycle. But it is interesting to think about, when do technologies reach this critical inflection point where you can they're effectively vulnerable for disruption, and the correct incentives and the correct metrics exist for a new technology to displace them. So in the interest of time, I'm not going to go into deep dive into the details of flash hard disk drives and tapes. So I encourage you to read our Hot Storage 2020 paper. For more, I linked it here in the slides, but I'm just going to summarize very quickly kind of where we see the existing technologies today. For flash, we believe it's approaching maturity. The way to increase density in flash in the last few years has been mostly through linear stacking, so stacking many layers of flash chips, which results in linear density scaling. And increasing the number of levels per cell only brings marginal density improvements, which means that, and in addition to that, decreasing the feature size, so being able to scale density quadratically, fundamentally ends up decreasing flash endurance. So you have this very complicated trade-off between number of layers, which only gives you a linear increase, number of bits per cell, which actually has very marginal improvements as you keep doubling the number of signal levels that you need to be able to tell apart, and decreasing feature size. And it's very difficult to see, given that most of the gains are coming from linear density scaling, it's very difficult to see how exponential growth can be sustained over the next decade. We believe hard drives have already reached maturity. If you look at the rate of density improvements, these have stalled for way over a decade now. But the bigger problem with hard disk drives is that their form factor that has write and read capabilities coupled with the media and their mechanical design fundamentally limit the I/O rates, that is the IOPS per terabyte that you can get from an individual hard disk drive. And this problem will only continue to get worse as the density increases, which will leave stranded capacity in each unit. And the only way to get back that capacity is to effectively scale out. For tape, it's unclear if maturity has been reached in terms of raw density. However, the number of tapes shipped every year continues to decrease. Tape libraries are a very niche and shrinking market. So in the past, for context, you had about 6 tape manufacturers on the market. Now that's only shrunk down to 2, Fujifilm and Sony. And in the US, they were suing each other a few years ago, and only one of them was allowed to sell tapes. When you're a cloud provider and the future of your service depends on an external and shrinking ecosystem, this is not very good news. So, it's unclear in general if the economic incentives exist to continue driving meaningful innovation in the tape ecosystem. And I'm going to talk a bit more about that later in the talk. So, what does this, and again, I encourage you, to deep dive into, if you're interested, to kind of read more about our paper, where we talk a bit about, in more detail, about all of these trends that reach us to lead us to believe, these conclusions. So, what does this mean? And, what can we do about it? Well, one interesting thing is that in the cloud, storage tiers are actually virtualized. So a customer doesn't buy a particular technology. A customer doesn't say, I want to store my data on flash. A customer buys an SLA. So a customer buys a certain SLA in terms of IOPS, cost, durability, latency, throughput. So the point is, the customer buys the SLA, not the actual technology. So in order to minimize cost, a provider can actually choose whatever mix of storage media they want to underpin a particular tier, as long as that storage media can support the SLA that the customer is paying for. Now, as technologies migrate across their S-curve, the storage that underpins those tiers can actually change. And we're already seeing this today. So flash is displacing hard disk drive workloads. And as hard disk drives become marginally cheaper over time, they're starting to displace tape workloads. Which the consequence of this is, of course, is that a technology has to remain competitive in order to have its share of the market eaten by other technologies, both old and new. And mature technologies will find this increasingly difficult as they're reaching kind of the end of their life cycle. The other interesting feature is that tier virtualization also presents a unique opportunity to bootstrap a new storage technology. So in order for a technology to reach takeoff, you have to generate sufficient demand to get enough production volume to drive the cost down. So, if you go to a component vendor and you say, I want 10 foo-bars that do something, they will come back and they'll say, right, each of them is going to cost you $1,000. If you go and you say, I want 100,000 foo-bars to do something, they'll come back and they'll say, right, that'll probably be $10 a piece. So you need to generate enough volumes to be able to drive the cost down and commoditize the technology. In the past, storage technologies would have to generate this demand in other spaces, in the consumer space, for example. So hard disk drives were, they were used in mainframes, but they were also used in many desktops. Flash costs were driven down primarily by use in not just enterprise environment, but also phones, cameras. They were used across many, many markets. Now, the unique thing about the cloud is that cloud providers already have this demand, right? The scale of demand for cloud storage is already big enough that individually, each of these tiers is big enough to generate the demand to drive the per unit manufacturing cost of this technology down. And again, given that tiers are virtualized, providers can actually transparently deploy a new technology to underpin existing tiers, and then build up enough demand and volume to actually commoditize that technology in the long term. So for archival storage, for example, a provider can transparently deploy a new technology like silica or DNA side by side with tape, provided again that it can meet the SLA that the customer is paying for, and effectively drive up the scale of the technology to commoditize it long term. And of course, you can also offer new tiers that are underpinned by a completely new technology. So if you're going to offer a new storage technology specifically built for the cloud, how should you do it? Well, one of the very important aspects, hugely important aspect, particularly from a cost perspective, is to avoid stranded resources. So these are basically resources that you paid for, but they're not utilized. They're sitting there idle, and the cost, the cloud provider has to cover the cost for them. And one important mechanism to achieve this is disaggregation. Now, when people hear about storage disaggregation, people typically think of this, which is what we call infrastructure disaggregation. So here, your storage racks are separate, physically separate from your compute nodes, and the storage is accessed over the DC network, the data center network. Now, this is good in that it lets you multiplex your storage across different workloads, but it still relies on a lot of these very expensive and general purpose storage servers that do nothing but mem copies to service IOs. And the challenge, another challenge of this kind of design is that the ratio of CPU and memory to storage is actually fixed. So as workloads evolve and data ages over time, these resources can start to become underutilized. There's another level of disaggregation, which we've experimented with here in the lab, which we call hardware disaggregation. So we've experimented and actually shipped disaggregated designs at the rack scale. So in this particular case, you have a very small number of storage servers and drives that are dedicated, that are disaggregated and also dynamically reconfigurable into different resource pools. So this lets you conveniently scale the amount of CPU and memory that every resource needs to kind of right size to the workload demands at any given time. But it doesn't reduce wastage inside individual storage devices. So remember, I was talking about the form factor problems of the mechanical design of hard disk drives and the fact that per hard disk drive unit, you're getting a decrease in IO density over time. So despite the fact that you're able to better calibrate your CPU and memory to the particular workload, you're still stuck with wastage inside each individual drive. And the only way to overcome this is to basically scale out. So you just have to buy more hard disk drives to cover the IO rates that the workload actually requires. But in the process, you end up with stranded capacity that's not accessible at the same IO rates. And the problem really comes from the fact that you can't scale the IO rate separately from the media. So we believe that a cloud-first storage technology should be designed to be what we call fully disaggregated. So every resource and functionality across both the hardware and software stacks should be designed to enable elasticity and maximize utilization. Now, what does this mean? It means that ideally, in order to best fit the needs of the workload, we'd be able to scale the media independently from the writers, from the readers, but also from the compute requirements, right? And one interesting feature of this is these little C boxes are basically your write stack and your read stack. And one interesting feature of this is that disaggregating this and effectively running the software on kind of arbitrary silicon lets us also better match the needs of the software to the particular silicon. So for example, we can use custom low power ASICs. We can use machine learning accelerators. I'll show you later an example where machine learning is actually used for signal processing. And one of the great things about machine learning today is that a lot of people are investing a lot of money in it, particularly on the hardware side. People are building more and more accelerators to drive down the cost of ML inference, increase the power efficiency. And so by running your software stacks disaggregated from the actual hardware, this means that over time, the cost of doing the same processing actually decreases over time. And in fact, today in the group, I'm not going to have time to talk about it, but we're also exploring a new technology that can potentially replace hard disk drives and provide this ability to scale the IO rates independent of the media that's actually deployed. Now, of course, you might look at this and you might say, you know, is all of this complexity worth it, right? You've just taken a more monolithic design over here and you've made it into a distributed system that's probably a lot more complicated. You know, is it actually worth the cost savings, right? But Really, it is, right? When you're running hundreds of DCs across across the globe, even a 5% improvement in efficiency or a 5% decrease in the amount of wasted resources in your data centers will actually translate into millions, if not billions, of dollars worth of savings. So, we believe disaggregation and kind of cloud-first design, or rather full disaggregation, as we've described it here, is really crucial to cloud-first, to designing storage technologies to be cloud-first. The other important aspect is, we think it's really important to embrace form factor freedom. So, new technologies that are designed solely for data centers shouldn't emulate existing hardware form factors or software interfaces, right? In the consumer space, form factor compatibility was very important, but in the cloud era, it really doesn't matter. All that matters is whether you're able to service the customer requests via whatever API you've agreed on with the customer at a given SLA. And the only hardware restrictions that you really have is that hardware deployment is done at rack level. So you just need to be able to fit in the loading docks of the data center and the power budget of each individual rack. And a cautionary tale for this is tape libraries. So the mechanical and system design of tape libraries dates back to the 60s when they were made for disaster recovery, and they are very inefficient and prone to failures. If you actually study tape workloads in production, the drives have abysmal utilization rates. They spend most of their time spooling tapes and waiting for robots to load and unload, rather than actually doing useful I/O. So, a cloud storage technology shouldn't cling to these antiquated designs and compromises that were made because we're now deploying technology in a new setting. Hardware, the fact that you're co-designing the hardware and the software together means that you can now optimize for the end-to-end tail latency of the system rather than average latency, which is very important because in an environment like the cloud where you're trying to multiplex so many different workloads in order to drive up the utilization of your hardware, providers end up having very little insight into the workloads. So when you're designing a cloud storage tier, you really need to provision for the 99th percentile latency rather than the average. And today, doing this is mostly leaves you at the mercy of software-based solutions that rely on whatever information the hardware, the storage device that you're working with chooses to expose to you to work with. I already mentioned this point, the fact that over time, disaggregating your stacks from your compute means that you can kind of ride hardware trends as hardware becomes cheaper or more efficient. But lastly, and this is more of a kind of operational point, we think that multidisciplinary teams are really key. So traditionally, the way that technologies are developed is you have different groups that operate in different communities and they work on very different layers, right? So you have physicists and materials processing people that will work on the actual media. You then have EE groups that will work on things like packaging and the memory controllers, and then CS groups will build software stacks on top of it. And this kind of isolation often can lead to emulation approaches where separate layers are very individually optimized and often made to conform to a certain interface. But there's actually no one ever takes the time to consider what is the end-to-end goal of the entire storage system, right? And kind of optimize across all of those boundaries. Because in a cloud setting, it doesn't really matter whether you have a block interface or a byte interface. It's your choice really, or you can design a totally different kind of interface to access your media. What really matters is, what is the API and the guarantees that we're providing the customer at the highest level of the system. And this kind of cross-layer optimization is hugely important to being able to extract the most from from the media. So on silica, for instance, which I'm going to talk about in a few minutes, we have a mix of physicists, optical scientists, chemists, electrical engineers, mechanical engineers, designers, systems people, machine learning people, and of course, as you might imagine, it's not always easy to break communication barriers, but we found over the years that leveraging and combining the strengths of each of these fields, we're able to progress much, much quicker and come up with much better solutions, right? And more creative solutions often to the technical challenges that we're actually facing. So I think this is, really important when it comes to kind of building the best kind of new technologies that you can. So, what's next? We've just been rambling for the last half an hour about how, poised for disruption everything is. So, what might happen tomorrow? Well, in the flash space, it's very interesting. There were several persistent memory technologies that were proposed over the years. The front runner for a long time was 3D XPoint, but maybe those of you who are keeping up with the news lately have seen that Intel is kind of halting production on XPoint and divesting away from it, which is maybe not surprising. At cloud scale, you can get persistence at byte addressable persistence. You can get it using just batteries, DRAM, and flash. And XPoint was offering lower densities than flash and worse latencies than DRAM. So it's not really clear, how is replacing DRAM and flash going to pan out given the properties of that technology. Hard disk drive maybe will be displaced by flash further. Again, if flash continues to go cheaper, maybe hard disk drive workloads might be displaced by that, or maybe a new technology that's not mainstream. So for example, something like holographic storage may become relevant again in the cloud era. This is something that we're working on in the group as well, but I won't have time to touch on today. In the cold storage space, tape is likely to be displaced by silica in the near term. But in the long term, maybe DNA can offer very high densities, assuming that the correct storage systems can be built for it. And one of the big pain points there today is that the dollar per megabyte even to read or write is astronomical. And driving the cost of that down, well, there are many other problems with DNA storage, but driving the cost down is several orders of magnitude is first and foremost the key thing that they need to address. So these are just some of our current thoughts, but for the rest of the talk, or of course, yes, something completely new that we haven't even considered might come along. But for the rest of the talk, I'm going to tell you what we're doing about this in the context of Project Silica, because I guess I've just been rambling about principles and observations and high level stuff, but I want to actually show you some cool tech that we're working on. So do people have questions up until this point? This is a good time to ask questions if you're confused or disagree with anything I've said. Yes. I see someone with their hand up.
I'm just handing over the microphone, which makes it easier to communicate.
Thanks. So my question is, how much, or do you have an estimate how much overhead there is for full aggregation compared against infrastructure aggregation?
I think it really depends on it depends. So yeah, it's a great question. I think what I showed here is it's a framework to think about how to build a system. It's not a concrete answer. I think people should aim for this. Now, where exactly you place the compute, it maybe the correct answer is that it doesn't always need to be completely disaggregated. It doesn't always need to be accessible via a network. Sometimes it makes sense for it to be co-located with the read head. It makes sense if the utilization of the compute to be high, or you have a latency target that you really need to hit where you can't afford to actually go over a network, or so I think the high level point is that this is what you should be aiming for, but this should primarily be driven by the considerations of what SLA am I trying to achieve, right? So what SLA am I trying to achieve? So am I going to have very tight latency requirements and what are the sensitive points of my system in terms of cost, right? If one of these pieces is really expensive, then you want to drive its utilization as close to 100% as possible, right? And disaggregation and multiplexing is the mechanism to do that. So does that make sense? It's not that there's a clear answer, like do hardware in this case, it depends on what is your media, how do you read, how do you write, and I'll show you an example of this in the next half an hour. Does that make sense?
Yes, maybe just a short follow-up question.
Yep.
Does more aggregation always force more overhead?
Not always. If you have a workload that's quite steady over time, then it's possible to right size the system to maximize its utilization. I think the challenge is that it gives you very little flexibility over time. It gives you little flexibility to adapt to changing workloads. It gives you little flexibility to adapt to growing workloads, but also to changing workloads over time. So as the ratio of how much compute and CPU and memory you need over time changes, CPU and memory to storage changes, it becomes difficult with this kind of infrastructure here to continue driving the system to be right sized. Okay, so anyone else? Otherwise, I'll just carry on.
Yeah, maybe one question from my end. So if you go to the full disaggregation, you just said it's nice, let's say, a pattern to think about how we would design storage, right? From a technology perspective, where do you see what technologies would support this more composable storage?
So I'm just about to describe one.
Oh, yeah, that's clear. The question was also from current trends. There might be also, do you see also CXL there as kind of enabler for that, or just to get an idea?
Yeah. So, for example, the holographic, the holographic data, which is something that is also exploring in the group, which is targeting kind of the hotter end of the spectrum. I think this is also so holographic is very interesting as a contrast to silica, because holographic storage, because it's a hotter access, it demands hotter access rates. It sits in a different point in the disaggregation space. So it's in terms of where do the compute requirements for the software stack need to sit in order to provide the low latencies. It sits in a very different point from something like silica, which is archival. And so it's basically, it sits in a different end of the spectrum in terms of how closely should each of these different components and modular blocks be deployed given the SLA of the system. But I think ultimately it's about what is the design that will get you the highest utilization and lowest cost. And I think that's ultimately it's, at the end of the day, it's about the cost. So we do talk a bit more about some more examples of this in the paper for existing technologies as well. But does that answer your question at all? I think ultimately it's about you have to take into account, I think, everything from the base properties of the media as well as the SLA that you're trying to provide with the tier to kind of find the correct design point in this space.
Yeah, no, totally. Thanks.
Okay, so I will tell you now a little bit about silica. So obviously I've been rambling about storage, but specifically thinking about archival storage. Why is archival storage so important, right? A lot of the stuff that we do is ephemeral, but a lot of the data that we generate as a species, it's either personal data or medical data or financial and industrial data or scientific data. Really, a lot of this data is actually very essential to kind of the preservation of our collective output in the context, in the case of scientific data, but also as our individual identities, right? Personal data, medical data. Some of this has to be stored for regulatory reasons. Some of it needs to be stored just to preserve our identity as a species, really. And as humanity continues to evolve and grow, this need will never go away. Unfortunately, we do not have a sustainable storage technology to meet this need today. The most cost-effective way of storing large-scale cold data is magnetic media, like hard disk drives and tape, with tape offering the lowest dollar per gigabyte cost for archival storage. Of course, the problem is that magnetic media degrades and is susceptible to interference, which means that in order to keep long-lived data around, every few years you need to copy the data over to a new physical media in order to make sure it's durable and it's persistent and accessible. With hard disk drives, this is on the order of 5 years. Tape advertises lifetimes of around 20 years, but the reality is that because of industry pressures and the lack of backwards compatibility between tape drive generations and physical media, economic and incentives and pressures from the tape industry is actually driving this cost down to around 10 years instead. The other problem is that because the media degrades over time and is susceptible to interference, you actually require expending energy in order to scrub the media. So those of you familiar with storage systems, will know that storage systems periodically will read the data back, recompute any sort of checksums that the data that's used to protect the data. In some cases, use error correcting codes to fix any residual errors that have accumulated and make sure that the data kind of stays over time at the same level of durability. So, of course, the consequence of these properties means that now the emissions, the energy, and the cost to store long-term data will scale with the lifetime of the data rather than any sort of operations that you perform on it. And in the group, we've actually spent the last 6 years thinking about how to build the best long-term archival storage technology for the cloud. And we believe that the answer to that is glass storage. So why glass? Why is glass the ideal media for archival storage? It's low cost. It's made out of sand. It is durable, which means that it just simply the media itself doesn't degrade over time. It's EMF proof, so it's not susceptible to interference from magnets, from electromagnetic pulses, solar flares, things like that. It's a warm media, which means it's impossible to overwrite even by accident. And it offers lifetimes of tens to hundreds of thousands of years. So this gives us really a truly sustainable media where we can leave the data in situ forever. And I think I've already convinced you now that the cloud has both the scale and the geo-distribution to offer low-cost storage at similar availability to existing storage systems. So I will roughly go through kind of 4 different high-level bits, which is how do you write the data in glass? How do you read data from glass? How do we build an actual storage system? And then talk a bit about durability and availability. And it's roughly going to follow, what does a day in the life of a silica glass platter look like? So to write the data in glass, we use a femtosecond laser. So this is a very short pulse laser. People think of lasers usually as a continuous beam. This is an incredibly short pulse on the order of 10 to the minus 15 seconds. Very high power, and you focus it inside the glass material. So you're not writing on the surface, you're writing inside the bulk of the glass material. And when you fire it, at the point of focus, you get these little nanostructures that you're seeing here, scanning electron microscope images of 4 individual voxels. And depending on the polarization of the orientation of the electric field of the pulse that you use to write, you can actually control the orientation of these little nanostructures inside the glass. And so by doing this, you can actually achieve multi-bit writing in the glass. And so here you're seeing 4 individual voxels, and here you're actually seeing a data sector that's written with prototype hardware that we've built in the lab that has over 100,000 voxels in it, that then all of these get read together. So we write, when we write all of these voxels, we write them in 2D shapes that are optimized for subsequent 2D readout later on. Now, you might think that because we are a optical media that we spin, because we're an optical storage technology that we spin the media, right? But we've actually made a conscious choice to engineer as much complexity out of our system as possible. So we've actually chosen to not spin the media because spinning media is very difficult to stabilize. It's very difficult to operate at high RPMs. You need to wait until the media stabilizes before you're able to read and write to it. And instead, we've chosen to move the light instead. So to achieve high throughput writing at scale, we actually use beam steering technology. We use beam steering technologies to steer the actual laser beam across the surface of the media. And using this, we're able to achieve aggregate system level throughputs that are comparable to existing tape archive deployments today. So here you can see where we can write individual layers in the glass very quickly, and then we can write over 200 layers inside a piece of glass. So in terms of density, today we're operating at densities that are raw densities, so pre-ECC, that are much higher than LTO9 tapes, which is the latest generation of LTO tapes. So to put this into context, in a 2 millimeter thick square piece of glass, that's the size of a DVD, you can store over 7 terabytes of raw data. And we've actually stopped pushing on improving the density of the technology a couple of years ago, and we switched to improving throughput. So we still think there's a lot more runway there on pushing the density even further. And we actually use in silica, we use a different technology for writing than for reading. Of course, when we write, we don't write blind. We actively monitor and we control the write process, but we want, from a storage system point of view, we want the guarantee that the data is durable and readable before we flush it from whatever higher level tier that we're staging it in. So in order to do that, we do what's called a verify operation. So reading is done with a lower cost technology. The illumination is just regular light. And reading is done by focusing on the layer of interest that you care about, and then reading an entire 2D sector of data at a time. And what we do basically during a verify operation is after an entire platter has been written, we basically read the entire platter beginning to end, and we make sure that the data is safe, is durable, we can decode it. But before we actually declare a write as durable. Now, an interesting property of the fact that the reading is different than the writing is that the illumination being regular light means that we actually can't overwrite the data even by accident. So with existing technologies, we know that this is actually a big pain point for customers, is that sometimes during this refresh cycle that they have to perform, where they copy data to new media, they actually lose data sometimes because of bugs in firmware, because of in some cases even for individual installations that manage their own archives. Sometimes they're even infected by malware that causes their firmware to accidentally delete their data. So the fact that we actually use a different reading technology that makes it impossible to overwrite the data is actually also a huge plus for the technology. To decode, we actually use machine learning. So for those of you who have some experience or interest in computer vision, we use a UNet, which is traditionally used for medical image segmentation. We have our own custom version of it. and we actually decode entire images at a time. So we basically take several images of an individual sector, and we feed the entire sector into the UNet, and we get probability distributions for all of the symbols inside the sector, which we then feed into error correction to decode, to fix any residual errors in the decode. And an interesting feature of this is that because we're decoding 2D sectors at a time, any increase in density will automatically translate into throughput increases as well, since we're imaging whole sectors at a time. Now, another advantage of technology compared to tape is that, unlike tape, where you have to spool and tapes are over 1 kilometer long inside the actual cartridge, and you need to wait sometimes over a minute for the tape to actually spool to the point where you want to start reading. Silica is a very fast technology. You can just seek to a particular location that you're interested in reading on the platter, and this is a very fast mechanical operation. You just read the data of interest that you care about, and you can eject the platter, which means you can service IOs much quicker. Now, I'm going to switch gears a little bit. I've showed you how we write, how we read, and I want to show you now how does the whole system come together. So this is just to give you a quick picture of kind of our evolution of archival storage design over time. In 1937, this is an archival library in Prague. You had a very simple mechanism for accessing media. You had this central gantry system with robots that couldn't move past each other, and they could only access a fixed number of media in these stacked drawers. And if you look today at an IBM archive tape library, it looks surprisingly similar. You have a very fixed gantry system in the middle with robots that can't move past each other, that are accessing media that just sits on a shelf. So there's been very little innovation in this space in pretty much a century now, and the net effect is very clear when you look at tape systems today. So when we designed the Silica Glass library, we actually decided to extensively study Microsoft's existing magnetic tape workloads and try to understand what are also the pain points of the existing technology today. And we came up with some very interesting insights, that some of which are actually go against the conventional wisdom in the storage community. We found that archival reads are actually predominantly very small. When people think about archival workloads, they think, disaster recovery, my database is gone, I need to get the entire full snapshot, consistent snapshot back. But actually, if you look at a production workload, the reads are predominantly very, very small. We found that the temperature of the data tends to decrease over time. So the access rate of the rate at which people access data tends to decrease over time. And as expected in the cloud, we found very high variability in terms of things like access rate across different deployments of tape libraries. And so this led us to come up with some key design principles that we wanted to follow in building the Silica Glass library. So first, the lifetime of the library should really match the lifetime of the data center. Because the media has virtually unlimited lifetime, and we don't need to keep refreshing and copying the data over to a new media every few years, that means that when a library is deployed, it should really be deployed there for the lifetime that the building is in commission. The second one is we wanted to go a step further than this worm property, the write once, read many property. We wanted to make it physically impossible to overwrite or corrupt the media, even in the presence of bugs or unintended software behavior. And this is a property we call air gap by design. And I'll show you in a bit kind of how we achieve that. And obviously, sustainability is a huge concern as well. We want to minimize the energy usage of the library over time, and this is particularly important as we know that the temperature of the data actually decreases over time. So, as the data becomes colder, the amount of energy we expend should also decrease proportionally. Because the reads are predominantly small, we also know that we need to minimize mechanical latency. That is, we need to minimize the amount of time that glass platters are spend in transit or being loaded into and out of readers, since there's many reads that we need to go through, because reads are predominantly small, so we need to switch between many different reads over any period of time. And because we know that you have this variability across different deployments, but also over time, we need to design the system to be modular and allow for deployment flexibility over time. And this goes back to disaggregation. So the first part of the library are these storage panels. So these are passive components. They don't require any electricity to power them. And you just leave them in the data center for the lifetime of the entire data center. So they're incrementally deployable. You can install rack size modules and then connect them together to get these long shelves that you're seeing here. And in order to minimize the amount of materials and energy that we spend, we actually store the media raw. We don't actually use any sort of cartridges or anything for each individual piece of glass. And the way we achieve the air gap by design property is that the shuttle network, so I'll talk about shuttles in a second, but basically writers are only accessible via this single rail that goes into the library. So it's physically impossible. Once a piece of glass goes into a writer, it's only ever accessible once it exits the writer. So it's physically impossible for anyone or anything to feed an existing piece of glass from the library inside a writer and potentially cause it to be accidentally overwritten. The next part of the library are these shuttles. So these move the platters around. So here you're seeing a glass platter being moved around, and these robots can move down these rails, but they can also do this crabbing motion where they move across the rails here. And they have a picker here on the side, which can pick glass platters into and out of storage slots and take them to readers in designated reader racks. And the key thing is that these robots are free roaming across the library, across the entire panel, the entire storage panel of the library, and because they can do this crabbing motion, it means that we effectively achieve all-to-all addressability between platters and robots, which is very important when it comes to failures. And I'll come to that in a few slides. This is actually a prototype of that shuttle design. So this is from our lab upstairs. This particular prototype doesn't have a picker, so it can't actually pick the platters, but the point of it was to experiment and demonstrate this crabbing mechanism. So you saw it unhooking from the top rail, doing a motion, moving onto the bottom rail, and then moving off into the distance. I'm not going to harp about disaggregation for too much longer. The media lifetime in silica is virtually unlimited, so it just doesn't make sense to package the read and the write capabilities with the media. But of course, we want to enable right sizing over the entire lifetime of the library, particularly as we know that archival data temperature decreases over time. A tape design where you packaged readers and writers together is also a terrible idea, because this means that the amount of resources you have deployed in the system has to be provisioned for the max of the ingress rate and the read rate in the system. So if those are vastly different, then that means that you have now underutilized resources. So what we did is we actually realized that the fact that our read and our write technologies are different is an opportunity, not a problem. So by deploying these separately, we can actually scale each of them separately based on demand. So we deploy the media incrementally as new data pours into the system, and then we scale the writers based on workload forecasting, and we scale the readers based on demand in the system. And again, we run the software stacks separately from the compute, which gives us many advantages, including the fact that And just to be clear here, by software stack, this includes things like erasure coding, encoding, and layout of the data. So remember I mentioned that we write the data in these 2D sectors, but the layout is actually optimized for subsequent reading. We have to do the ML decodes to actually retrieve the data back. And of course, like I was saying earlier in the talk, this has all of the benefits of disaggregating the actual compute from the hardware, which means that over time we'll end up benefiting from these new hardware revs and will actually decrease the cost of operating the system over time. And so over time, we envision a silica library growing by deploying different storage panels, each with a different ratio of readers, writers, and shuttles deployed based on the demand of the system. And over time, as the data becomes cooler and the workload changes, we can actually redeploy some of these resources to achieve right sizing over time. So the last thing I want to just briefly touch on is durability and availability. So failures do happen just like in any system. Readers and writers, we can deal with failures very similarly to today's systems. You can just have, you can basically service a malfunctioning unit while the current ones are being serviced without actually impacting the rest of the system. Library shuttles can at most only block several glass platters. So if a shuttle breaks down and it's in the middle of a shelf, it can only block access to the platters that it's sitting in front of. The solution, of course, to this is that we have this crabbing motion, which means that we allow all-to-all addressability in the whole system. So that means if the platter that we want to read from is blocked, we can retrieve the other platters that are part of the same coding set from a erasure coding point of view, read them back, reconstruct the data that we actually want to serve to the customer, and we still achieve availability in the system. In terms of error correction, we have 3 levels of protection. Per sector, we use LDPC codes. So this is low density parity check codes and checksums for integrity. This is the same kind of ECC that storage technologies use today. And this is really meant to protect against random errors in the raw decode. So just like any storage technology today has spurious errors in the decode, just from stochastic noise and whatever sensors you're using, we protect against those using LDPC codes. And we have another 2 levels of error correction across sectors, so within a platter, but across different sectors in the platter, and across platters. So within a platter, across sectors, this is to protect against cases when LDPC and checksum failures happen, which is extremely rare. And across platters, it's basically, in the cases of library shuttles, temporarily breaking down, and until they're serviced, you still need to be able to access the data that you want. And actually, for erasure coding, we're not using a conventional storage system code. We're actually using network coding. So this is something that dates back, that was very popular in the peer-to-peer days of content distribution in networking. And we're actually exploiting the worm properties of the media to, using network coding, we're able to actually get much quicker reconstruction with lower overheads using network coding compared to conventional erasure coding schemes like Reed-Solomon, for example, for storage. And in total, we're actually able to get combined overheads across these 3 levels of error correction that are lower than today's tape systems. So that's pretty exciting. So, I kind of showed you all the different parts of the system and how everything comes together. And, I think I genuinely believe that, 50 years from now, when you decide to read back one of your old photos, this is what it's going to look like. You're going to have one of these racks waking up from one of these robots waking up, doing a small read for your data, serving it back to you, and then going back to sleep, and effectively expending no energy otherwise. So, yeah, that's it. That's it for my talk.